Thank you everyone for joining us. This is our monthly seminar brought to you by the NASA Cosmic Origins Program's Galaxies Science Interest Group. So the group has been formed for a few years, but for the past year, it was a bit quiet. So we're trying to restart this seminar series ahead of the exciting the Great Observatories and also the Habitable Worlds Observatory. So this is why we're bringing you this monthly seminar. And we have talks lined up for the next year and the next summer. But hey, if you're interested in giving a talk, just reach out to me or Benny. We can always keep extending the schedule and start filling next year's schedule. So especially I encourage junior folks to join us because Hab World is not going to be in the sky for another 20-something years. So yeah, this is your telescope. As much as getting knowledge transfer from the established generation. Great. Okay, so today we are going to hear from Aaron Smith, but before that, Swara has a quick announcement to make. So let me start sharing the slide, and Swara.
Hi, everybody. Thank you for joining the Galaxies SIG seminar. So my name is Swara Ravindranath. I am the Deputy Chief Scientist for the Cosmic Origins Program at NASA Goddard. I'm just going to take a few minutes here to tell you about a new solicitation from the Cosmic Origins Program Office. We are looking for your input to define precursor science gaps for the future NASA flagship missions. So this is in connection with the ROSES 2023 call for astrophysics decadal survey precursor science gaps. Your feedback will definitely be helpful to determine how these ROSES precursor science proposals will be evaluated, and hopefully some of your own, because I'm assuming that you will put in proposals in the area of cosmic origins research for the precursor science proposal call. So the solicitation that the Cosmic Origins Program Office has is requesting your ideas for science gaps, which we will use to create a precursor science gap list. And you can find more information about the ROSES call and about the precursor science gaps, how we define a precursor science gap. That information is given here in the link here, which is you can go to it from the Cosmic Origins website, go to the Communities tab, and if you look under the menu, you have the precursor science gap, and that's the link that's provided here. There is a Google form on that page, and this is the URL for the Google form. So you can contribute your ideas here on the Google form. And once we receive your inputs by the deadline, which is November 17th, the Cosmic Origins Program Office will compile those results and review them and make the complete precursor science gap list available for the community to inform them when they write the proposals for the ROSES call. The ROSES proposals are due in April 2024. And if you want to take a look at the science gap list that was prepared for the previous year for the ROSES 2022 call, you can find that on the link that's provided here. All of this information is also available on the Cosmic Origins website. Again, just go to the Community tab, and then there is the link to the precursor science gaps. So I strongly want to encourage you all to submit your ideas here and make your ideas count. And if you have any questions about this, please feel free to contact the Cosmic Origins Program Office. You can contact the Chief Scientist, Peter Krasinski, or you can write to me, and our email addresses are also provided on that link. So so we need more input on the Cosmic Origins science, so strongly encourage you to please provide us your feedback and submit the proposals for the ROSES call. Yeah, thanks for your time.
Thank you, Swara. Thank you. So I'll make sure these links are later copied to the chat, so you can access these. Maybe we should also post them on the Galaxy SIG website.
Absolutely.
So Yeah, this is super important because the next great flagship is now named Habitable Worlds Observatory, despite that it is a general purpose, general astrophysics observatory. So it's really important to make sure it meets the capability that this community needs to look for galaxies at every step of its development. So this is why we're doing this. We're trying to figure out what kind of science do we want to do in the next 10 to 20 years, but also to make sure that our voice is heard and the telescope can do whatever we want it to do. Okay, so with that said, please contribute your ideas. And next, without further ado, Aaron.
All right, can you see this all right?
Yes.
Okay, great. Thanks so much, Aaron, for hosting this and putting this together with Bene. Yeah, so today I'll talk about emission and absorption line modeling from HydroSims. So this is a kind of a difficult topic, and I'm sure there are many experts who, on the observational side or the simulation side. So this is mostly intended to kind of help brainstorm and get some ideas flowing. So I'll go through a bit on observations, simulations, some radiative transfer, and then some outlook at the end. But first, the basics, of course. On the left, we have a continuous light source, like a star, for example, and this might emit something like black body emission. So it's pure continuum. But if this light actually interacts with a gas cloud, which is pervasive around galaxies and throughout the universe at various scales, then by ionizing some of this gas, by heating it up, you can actually produce emission lines from this gas. So that's what's shown in the middle. And then on the right, if you are absorbing against the continuum through a cold cloud, then you will actually absorb these features. So a bit on the modeling side, we'll get more into that, but this is the kind of the basis for the rest of the talk. But it's important to know that these lines are critical diagnostics for galaxy evolution. So I tried to be a bit verbose in case people want to go online and look later. It's more useful. But essentially, these photons in emission are created by directly converting the ionizing photons from stars or AGN into recombination emission. But there are a number of other lines, especially metal lines, that are dominated by collisional excitation and thermal processes. And beyond this, they really are directly telling us the star formation rates. They may be biased, and I'll get into that, but there's age, metallicity, dust, temperature, kinematics, and so forth. So on the absorption side, you're really probing, again, I said all these scales, the ISM, the interstellar medium, circumgalactic medium, the intergalactic medium. And this is kind of a recurring theme, and various lines are better at doing this differently. So the figures on the bottom are kind of basically from the literature, various papers using line ratios as diagnostics and looking at the properties there. So I think it is important, though, to kind of go back to the basics. So I'll show some schematic understanding of this. So within an H2 region, an ionized region where you have these young stars, you have Lyman continuum photons, and they may escape that local cloud, the birth cloud. They may even escape the galaxy, or they may be absorbed by dust or helium before ionizing hydrogen. Both of these lead to conversion losses. But once you do ionize hydrogen, either in the diffuse gas or the compact H2 region, you actually will produce this recombination emission, which sends out the photons that we want. And then we have to be able to model that process. So this is reprocessed light. And so I'll get a bit more into that later. But when we observe this, it's the result of complicated scattering physics, dust, ionization, the geometry, and understanding kind of the star formation histories, dust, metallicities, and so forth. So beyond this, from the observational side, it's been increasingly common to have IFU spectroscopy. So this means that you're not only spectrally resolved, but you're spatially resolved as well. So for every pixel, you have a spectra. Essentially, there's been tons of breakthroughs looking at wavelengths that are really good actually for high redshift observations for various lines, or low redshift H alpha, for example, higher redshift Lyman alpha. So the Habitable Worlds Observatory, HWO, will kind of allow us to do this for Lyman alpha emitters at low redshift. So the bottom three galaxies are from Lyman alpha reference sample, where very rich detail of local galaxies using the Hubble Space Telescope. And on the right is kind of precursors of what's been possible with MUSE, for example. So a bit wordy, but the case for an IFU on HWO is really that you have to do the UV from space for certain science. The absorption, the Earth's atmosphere just absorbs too much. The high resolution allows us to avoid line blending and confusion. And it's also kind of carries on this legacy, right? We want the UV, optical, and infrared. And so I'll leave the emission and absorption, kind of move on from this, but there is a rich subset of physics that both of these probe, and they're kind of complementary. Okay, so now for the simulation side. So first, to get some feel for the landscape here, there's this review by Mark Vogelsberger where there's this chart. So on the top and bottom, the separation is that we have zoom-in simulations where you get rich details of galaxies on the top, and the bottom row is large volume simulations. So you're getting many rich galaxy statistics, but the information for an individual galaxy might be kind of lower resolution, for example. And then left to right is the dark matter only runs, and on the right includes the gas dynamics as well. So this is a couple of years old, so there's newer simulations as well that aren't on here. But the kind of the feel is that as a community, we've kind of come to consensus about dark matter only simulations. There's still a lot more work, of course, that needs to be done. It's not a closed book, but we feel that we understand the properties that come out of this and the numerics involved. On the other hand, the hydro sims, there's disagreement between groups. There's disagreement in approaches. The methods are much more complex, and understanding the cooling physics, multi-phase ISM, feedback, black holes, and all the other physics can be a lot of work, and this is multi-year efforts from large collaborations. But I do want to give some sense of hope here. This is kind of a hero simulation from Bill Hopkins and the FIRE collaboration. And this movie, the amazing thing about it really is that it covers about 9 orders of magnitude in scale. So typically in a simulation, you're lucky to get, you can get 4 or 5 quite easily, but to kind of double that, the number of order of magnitudes, you're really kind of using a stepped ladder approach here. And you can see in the upper right, the cone kind of walks through those scales where you have the black hole jet. This is specifically targeting accretion on a black hole. And then kind of the gas environment leading to that, to the accretion and so forth. So, there is tremendous progress here. It's not, not that we're completely hopeless, but for example, you're not able to get this kind of resolution throughout the entire simulation, throughout an entire galaxy. That's beyond us at this point. So as far as modeling emission lines goes, so you have, of course, all the complexity of the simulation. But these simulations are kind of intended to help plan and interpret observations. There's, of course, all the rich physics at various different scales, and we need accurate models to disentangle what's going on. All of the simulations are essentially mocks. They're not perfect representations of these processes. There's corners being cut, or approximations being made, and it just depends what different groups are doing. But when it comes to lines, it's more stringent in the requirements. You need to really consider the ionization states of, for example, hydrogen, helium, and metals to capture this correctly. So the cartoon on the bottom is kind of that you have your simulation. Okay, maybe you got it from somewhere, but then if you were to think of this in terms of the physics, then you would need the ionization states. Maybe that's given to you from the simulation, and then you need the emission line fluxes. And again, this can also be done on the fly in certain cases. So just briefly, this is kind of a step-by-step of where we get to. There's kind of advantages and limitations, mostly in terms of accuracy versus computational cost. So this next slide kind of goes into that a bit more in a bit more detail. So the goal here is to actually understand what the assumptions are when you read some kind of simulation paper. What are they doing? So on the left, you can actually take the star particles from the simulation and essentially have some generic templates that are being used, some various approaches to this. But the point is that you're essentially using only the information from the stars. Maybe you're getting some information about the gas around it, but it's essentially a star property. So this is very efficient. Okay, maybe not running a million cloudy models, but if that needs to be done once, then people do this. But then, of course, then you have this way to do this mapping from the stars. So this can also include like dust RT post-processing. Any of these approaches can like add layers to this. But for example, if I want to get H alpha, in this case, the H alpha is coming from the star particle. All right, so moving on to the gas, it's essentially the same idea, except that the information comes from the gas particles. But there's still some type of modeling that is kind of bridged to get there. So you can use cloudy mappings, FSPS, SCIRT has procedures. There's various things that can be done in post-processing. Chemistry chimes, for example, or just some machine learning algorithm trained somehow. But the idea is here now you're making slightly better connections to the gas dynamics as well, but there are still limitations, of course. So the final column here is the on-the-fly radiation hydrodynamics. There are kind of an increasing number of groups, but it's still relatively small community. The ionization states themselves are calculated during the simulation. There's additional memory and CPU overhead for each species that you model and each energy bin that you model, and the accuracy of the physics. It's very easy to get some of these things wrong, and people deeply involved with that are struggle to kind of I guess the way that I explain this is actually when you add more physics, it kind of makes your life more difficult. The complexity kind of seeps into every aspect of it. So, you know, if you thought that the stars was difficult, okay, maybe it's difficult because you don't know enough information. But doing it on the fly brings this as well. But there's good groups, and this is in almost all the state-of-the-art codes now. So a question is, do all roads lead to Rome? So at this point, no, there's no community consensus, as I said, but you know, given the complexities that we're looking at in terms of accuracy, numerics, and so forth, we need to kind of advance the state of the art across multiple methodologies, from the simplest to the most, you know, comprehensive, expensive ones. So to kind of put this in perspective, all of these galaxies here they were all generated by AI from, you know, some image, and then kind of tweaked in some way to highlight the different features. Maybe they're too idealized, or very unrealistic, or too diffuse, too clustered, point-like, or whatnot. But you know, eventually our goal is to get some kind of approximate consensus that, you know, the one on the right kind of looks a little bit better. Maybe it's not the galaxy you're trying to model, but looks better. So this here, as I was thinking about it, all the pitfalls that can happen with simulations, you know, to be transparent about this, you can kind of list them. I put some description, I put some consequences, and then some justification of, you know, it's not that we're trying to get things wrong, but for example, if your pitfall is that your intention with established theory framework or observational data, this kind of undermines the credibility of the approach or the simulation. But the justification is that this is actually not such a bad thing if you're just doing some exploratory work to gain intuition, for example, or if it's the best guess at the time. So, you know, I'll leave this up. It was kind of fun to do that, but in interest of time, let's move on. So just like resonating this idea of a lack of community consensus, really this stems ultimately like from the different approximations that go in these models and the challenges that every model encounters. So, and I kind of want to emphasize, you know, again, these are very highly coupled problems. If you, for example, are concerned about the CGM, you increase the resolution out there. That's an incredible feat and incredible push. But the thing is that the galaxy, you know, star formation and feedback galactic winds, this couples to how the galaxy itself is modeled, and so, you know, it comes back, and, you know, likewise these simulations that are, you know, resolving this black hole accretion and all this, you know, the accretion onto the galaxy and the resolving these multi-phase winds is just not, you know, happening unless it's really targeted at that. So, in interest of that, I think, essentially, if we keep pushing for these higher quality observations, and then this can kind of ground the simulations to reality a bit more. So a bit on my approach, because there's going to be some bias in this as well. I have this COLT code, which is Monte Carlo radiative transfer. The idea here is that you really want an accurate treatment of the radiation field to really probe what's going on and interpret this, kind of take the simulation for its word. So it's not so important to understand the equation exactly, but the radiation field I intensity changes in time. Photons go in straight lines. There are some sources and there are some sinks, absorption processes. And then in some cases, with each scattering event, you can change frequency or direction. And the Monte Carlo method kind of captures this extremely well in post-processing. And again, even if you use some accurate method like Monte Carlo, you can still do this in a way that kind of sweeps things under the rug. So you have these unresolved H2 regions just converting some kind of line luminosity from photon rate, or you can again take the simulation, say believe what it resolves, and have this case B, for example, recombination rate between free electrons and protons. So this is kind of the latter approach is what we're discussing here. So this is a simulation done a few years ago by Raoul Kanan, and this uses a model that's very similar to FIRE in the REPL code. So you kind of have this feedback, but the real impetus here is that it's modeling the radiation on these galaxy scales down to roughly parsec resolution. So here we can apply these frameworks to these simulations that are kind of ideally suited for this because of the physics that's included. So we still actually do calculate the photoionization states in post-processing to compare and understand exactly what's going on. We get a little bit more detail from the Monte Carlo about where the radiation is going and all that. But then in the end, you can get these ionization states for every species. You can then get lines. So yeah, most of these aren't in the UV, but you can get all the UV lines as well, or target a different simulation where that's more ideal. But I can't skip what's going on here. The simulations just aren't resolving the early phases of H2 regions. These are extremely compact in very dense gas. They can be sub-parsec. Here, it's kind of a low density H2 region, so it could feasibly be resolved. But this is nice work by Jin 2022. Essentially, the point here is that when you compare some accurate kind of fractal turbulent model to the 1D expectation, some lines you get correct by design because of recombination balance. Some you start to deviate because the physics gets a little more coupled to the temperature and all of that. But others are kind of dominated by like boundaries, and you can see that this is not a sphere anymore, so you're kind of deviating quite a bit. Yeah, so I will skip this in the interest of time. But when you're not resolving H2 regions, there are ways to correct this on the fly, which are being incorporated or are in the codes, a few of the codes now. But looking at the simulation, just to kind of understand, what's going on, because the radiation field might go in different directions, and various other reasons. There can be gas that can be slightly over or under ionized. So basically, even though RHD gives the kind of the correct approach for feedback, getting good phase space structure, there are still some complications with lines, because these are like a density squared process, and so the part that you're resolving, just barely resolving, is always kind of the edge of what's dominating much of the physics. So something that we've been looking at is to kind of improve the resolution around young stars. So we came up with a scheme, which is in prep, kind of an aggressive adaptive mesh refinement for Voronoi tessellations in a repo, or in post-processing, for example. So the idea here is that if you have a grid, then you can kind of flag that cell for refinement. And what ends up happening is you can kind of add 3 points at each of the circumcenter locations, kind of the corners. And this allows you to kind of maintain the cell structure as it was before. But you kind of essentially have refined in a very similar way that the adaptive mesh refinement codes do it. So there are some caveats, because the geometry is complicated. You kind of want to avoid situations that will kind of lead to strangely shaped cells. So you can kind of merge this here. But essentially, your new cells kind of jump at least an order of magnitude in resolution, typically. So if you were to take an H2 region that's highly under-resolved and just throw resolution elements at it, just keep going and going and going. Now, this is a Stromgen sphere, an H2 region, that has been uniformly resolved by 100,000 cells in 3D. That would be a bit much for every single star particle in the simulation. So here now, this is the same situation, but we use this aggressive adaptive convergence thing. And actually, after 2 or 3 iterations, you're already there. So your basic line properties that get you, within 20% of the correct answer are already here. And of course, you can push this further and kind of get something that resembles the slightly different color bars schemes used here. But this leads to predictable convergence properties as well. So that's kind of one direction we're going. I just want to make a couple comments, because I think it's also important to go in multiple directions as well, to kind of interface with more communities and so forth. So this is a slide that comes from Cody Carr and Elena Henry. And so essentially what's going on here is you have an observation from HST where you had an absorption line in the UV, silicon 2. Some of this gets re-emitted as a fluorescent transition here. And then you can kind of make some partial covering model, which makes some assumptions, but essentially the velocity gradients are assumed. It's kind of a simple model, but then you can start inferring the mass outflow rates, for example, relative to the star formation rate in this one, and kind of get the landscape here. Now, there are ways, different levels of doing this, and kind of it's been recently kind of discussed that more larger parameter space models kind of work better than these low parameter space models. You can do this in this case in the fire simulations, and some of these features are well fit, mostly in models where there's a significant detection of outflow. If the line is very close to center, then the degeneracies in these models are not very good, not very constraining. So we're also pushing this with idealized cloud crushing simulations. Here, we take simulations by Matthew Bruzzo and German Fielding, Greg Bryan, and then we post-process this through the pipelines. We can then populate these wind models that kind of co-add the spectra in ways that can then be interpreted. So it's a kind of, I think I only have one or two more slides here. The future directions of simulations, of course, bigger, better, all of that. But the way we get there more efficiently is kind of by combining the strengths of different techniques. So these hybrid methods, or for example, optimized methods that really test when you need the accuracy versus the efficiency. But the elephant in the room is, in my opinion, is always numerical resolution. Just that's kind of a bottleneck in any of these methods. But it's going to be the next generation's all exascale and all this AI and everything. So ultimately, we kind of have this synthetic astronomer in a synthetic observatory in a synthetic universe, right? It's incredible. They can now model essentially full nuclear reactors in simulations. They don't have to build it. They of course will, but they don't have to build it wrong the first time. So in summary, this is the last slide, just kind of putting what I think are some areas to focus on in the next decade. From the simulation side, of course, enhance the physical realism. Second, develop the right kind of algorithms to handle the increasing complexity. Of course, observations will do this as well with the data analysis. Three, just make sure that the observational campaigns are designed to constrain simulations, so that we can actually say something about this. Four, it's this increased focus on breaking degeneracies by multi-wavelength spectrally resolved studies. And then five, we kind of want to support the community, kind of establish good practices, standards for sharing data methods that'll just help us get there faster. So yeah, be nice and all of that. So thanks for listening to my perspectives on this. I'll take any questions.
Thank you, Aaron. Thank you. And yeah, we can take a few questions, and I'd like to take this to structure more like a discussion, actually. That's why we save a lot of time after the talk. The talk is only filling half the hour. Great. Manek?
Yeah. All right. Thanks. It's a very nice talk, but I have two questions. So the first is regarding electron density. So are you assuming uniform electron density for your simulation? Because in reality, they could vary, right?
So yeah, this depends on the exact model that you're using. Some models will just assume, every H2 region is at the same density, whatever value they'll assume. But in our simulation, this is kind of self-consistently predicted from the radiation hydrodynamic solver.
So like, how's like the radial profile? Because I believe like when you go from like a galaxy's center to like outside, it might decrease the electron density. Like, are you like also kind of assuming like 1/r to the power n variation? Or like, yeah.
Yeah, exactly. There's you can study this and make some power law fits or exponential fits. That's typically how it goes for in disks. It's there's a ton of caveats here. Does your simulation have a black hole? Can you trust which part of the simulation can you trust? So as long as you're talking about the right thing, then I think it works to discuss in this context. But yeah, I mean, this is not a 1D model either. So yeah, maybe I can jump back to some of this. So in these type of models, the density will go as a power law, and also some kind of velocity as well. So this is the idealized model, but the hydro simulations are really, you're really getting some rich physics.
So my next question is regarding the mass outflow rate. So could you please go back to that slide where you're talking about outflows?
Sure.
I think there was a spectral profile you were showing. This one. So it was like not like super clear to me. So like, what was your conditions on like, the no outflows? Is that like only not having asymmetric line profile, or there's like more to that?
Right. So it's mostly kind of where this comes and hits very close to zero. Whereas, yeah, as you're saying, there's kind of some asymmetry here that you're picking up some amount of absorption from faster moving clouds. So the problem lies actually in the interpretation. This might be completely valid for what the simulation is actually saying, or it might indicate that you compare this against, for example, classy galaxies, that kind of legacy HST selected galaxies. You have to kind of consider what's going on in that sample. It's above the main star forming sequence. The star formation rates are quite high, which leads to very rich understanding of the outflows themselves. So as long as you take that into consideration.
Right, because I was going to add that, like, sorry, please go ahead.
No, go ahead.
So sometimes, the broadened line profile, not just, the asymmetric, like sometimes due to turbulence, the Gaussians, they get like a broader base, and sometimes they might look like Lorentzian. So it's because, outflows could happen in like, in different forms, right? So yeah, if there might be not just some asymmetric line profile, you might have like a broader base due to some turbulence going on in the center of the galaxies, or like whatever regions affected by the starburst or aging driven winds. So yeah, I mean, if that could be possible to include it in the model, would be great, because then we actually having like a more conditions to actually understand like, okay, this is the mechanism that might indicate there's the outflow going on.
Right. Yeah. So I think all of that is valid. There's certainly wider and narrower features going on here that are directly related to aperture size, what clouds you're picking up, the turbulence. So a lot of these simple models, there's no, this would only be kind of implicitly caught with the column density more, rather than they kind of are based on Sobolev approximation, which there's people that think a lot about this, and I don't.
Thank you for the question, Mike.
As much.
I think we should move on to the next question. Allison?
Hi, that was great. My question is super simple. You had a slide earlier that I think was your simulation where you had the same galaxy face on in different emission lines, and it was the slide, this one. What is this reference? This is amazing, and I've been trying to find the paper and I can't find it.
Yeah, I mean, just search for Smith and you'll find 1,000 people. No, you can put on, let's see,
Is this
Sandro
the paper that's
Cicella.
this isn't just the paper that's the release of the code, right? Or is that a, yeah.
It's more of a science and
Okay.
methods paper. So I kind of focused more on methods, and Sandro focused more on like observational interpretation, dust properties, and the diffuse ionized gas.
Okay, I'll keep trying to find it. I really want to find that paper. Those images are amazing, and I want to like stare at those for hours.
Yeah, well, I mean, it's getting better. There's always pitfalls in the things you did like 2 years ago, right? Yeah, we're happy to share data as well.
Great. I'm trying to look up that paper in real time and also failed. So Aaron, send it to me and maybe I can relay that, or you can send it to Allison directly.
Sure.
Great.
That'd
Any
be
other
great.
questions? So I have one actually. Aggressive AMR looks amazing. And I also want self-consistent model from end to end, but it's really hard to do. And now we're stuck with models like Cloudy or Skirt. I'm not super familiar with this code, but what is the most hand wavy or things that went into this type of model? Like what we do with dust and IMF. Is there something that bothers you in this model and can be fixed as precursor science before we get HWO?
Yeah, I mean, I think it's kind of like passes down one to the next. So it's not that that you just count up the stellar mass and then directly convert this to some H alpha. I think this was kind of like okay in the era of every galaxy is 1 pixel, but yeah, when we're doing this resolved IFU stuff, the surface brightness, I mean, even the way that the simulations are compared to observations can, doing the Voronoi binning that observers do and making sure that the noise is roughly consistent. Yeah, even that stuff affects it significantly. So from my perspective, it's been kind of interesting and fun to like take a simulation that doesn't resolve some of these features, but then try to push it to do this, and you start seeing convergence, and hopefully it's not some artificial convergence or something, but yeah, the next generation of simulations, I mean, they're coming, they're essentially here, but it's going to take us the fire and TNG and all of these models, they've been around long enough that they're pretty well studied, but the new physics is being added to every group, some faster than others, I guess. Yeah, I hope maybe that's not specific enough, but
No, that's totally fine. Yeah, something that keeps me up at night is we try to do a few things like training a machine learning algorithm on synthetic images that is made with some of these like TNG galaxies, and then apply them to real observations, and the results aren't exactly what we wanted, or is not exactly efficient or effective doing that. So it just prompts me that there are still some fundamental differences between the real observed galaxies and the ones that we simulate.
right, exactly. I mean, so this this table is, kind of what are you running up against? Is it, that the model was calibrated, or you get the right answer for the wrong reason, or you get out what you put in. This kind of sounds like what you're saying.
Yeah. At some point, we have all run into a version of these problems ourselves. So this is a great table. Thank you for making it. Make sure the slides and the recording of this talk is posted somewhere people can find.
Sounds
and
good.
If you're not already subscribed to the Galaxies SIG email list, please do. So when the slide talks are available, I can post them and make an announcement. Also, you will receive announcement for our next seminars. All right. Any other questions? If not, I'm sure people will be happy to get 10 minutes of their life back. All right. Thank you so much, Aaron, for giving the seminar. And hopefully all of you will join us in a month. Yeah, enjoy the rest of your day. And I'll post this recording of the talk online, and we'll send it out to the email list. Thank you, everyone. Bye.
See you. Bye.